Good afternoon, class. We are looking at Chapter 6, Exponential and Logarithmic Functions. Here, 6.6 Exponential and Logarithmic Equations. So in this section, we are going to cover the following objectives. Of course, we have covered the exponential functions, graphs of them, log functions, logarithmic graphs and properties, and now exponential and logarithmic equations. Use like bases to solve exponential equations, use logs to solve exponential equations, use the definition of a log to solve log equations, use the one-to-one property of logs to solve logarithmic equations, solve applied problems involving exponential and logarithmic equations. So reminding everybody that an exponential function is in the form of a to the power of x, where a is not 1 and larger than 0, and if it's between 0 and 1, it's an exponential decay. If it's larger than 1, it's exponential growth. And of course, if it's equal to 1, it is not an exponential function because it's a horizontal line. These are the properties. You remember, horizontal line is the x-axis, y equals 0. There is no vertical asymptote, horizontal asymptote. Y-intercept is located at 0, 1. X-intercept is none. Domain is all real numbers. Range is from 0 to infinity. So when a is positive, we are dealing, when a is larger than 1, we are dealing with an increasing function, where the limit of f of x as x goes to infinity is infinity, and as it goes to negative infinity is 0. If it happened to be between 0 and 1, that means this graph, we have an exponential decay, we have a decreasing function. The limit of f of x as x approaches infinity is 0, as you can see, resulting in a horizontal asymptote, and limit of f of x as x approaches negative infinity is positive infinity. So that's something to remind everybody. Also, the definition of a log, basically, log is simply an exponent. So we should be able to do this conversion here. X equals b to the power of y is y equal to log x base b. Both of them have the same base b. Both of them have the same power or exponent y. Logs and exponential functions are inverse of each other. For example, y equals ln x. Remember, when the base is, we use ln. That is equivalent to saying x equals e to the power of y. And y equals e to the power of x and y equals ln x are inverse functions, therefore symmetric with respect to the line y equals x. Y equals 10 to the power of x, y equals log x are inverse functions, therefore symmetric with respect to the line y equals x. As far as the notation is concerned, when the base is 10, we don't write it, we just write log. Y equals log x means x equals 10 to the power of y. And the best course of action to understand log is just follow this arrow. So log x base b equals y, or log to the base b of x equals y. That means b to the power of y must be equal to x. So that is understanding the concept. And with that, when we understand this, we can see the properties of logs, such as log 1 base b is 0, log b base b is 1, log b to the power of x of base b is x, b to the power of log x base b is x, and this is the product rule. Log xy is log x plus log y. All of them have the same base b. Log base b of x over y is log x minus log y. Both of them have x base b, and this is called the quotient rule. Log base b of x to the power of n is n log x base b. And for a common log, we can expand this, make the transition to common log. Same properties. It's a general form. It's a specific case. And for a natural log also, we can come up with those properties which give rise to, again, the same topic that was mentioned, that exponential functions and logarithmic functions are inverse of each other. Also, log x base b, we can use the change of base formula and write log x base a over log b base a. And either we go with the common log or a natural log to do the evaluation. As you can see from the graph, when x is between 0 and 1, the graph is below the x-axis, ln x is negative, and above that is positive. And this says both of them, the log and exponential function, have slopes of 1 at this point. That has got to do with the tangent line coming up in calculus in essence, so don't have to worry about it. What we want to add now, new stuff, 6.6 exponential and logarithmic equations. Properties for solving exponential and logarithmic equations are as follows. If we have a to the power of x equals a to the power of y, because we have the same base, we must have the same exponent, therefore x must be equal to y. If it's a to the power of x equals b to the power of x, because we have the same exponents, we must have the same base. That means a must be b. Same thing works out with logs. If x is equal to y, log x base a and log y base a must be the same. Of course, x and y, they represent the argument of logs, must be positive. If log x base a and log x base b are the same, then the base a and base b must be identical. And again, x is positive, a is positive, b is positive. So those are the properties we are going to use to solve equations. Three to the power of x is AD1. Most likely, you know, AD1 is 3 to the power of 4. Therefore, x must be equal to 4. Four to the power of x plus 2 is 1 over 16. Let's see if we can change any of them such that both sides have the same base. Notice this is 4 squared. So we can bring it up and make it 4 to the power of negative 2. Because they have both base 4, their exponents x plus 2 and negative 2 must be identical. Move this, x becomes negative 4. A to the power of x is 1/2. As you know, the left side, 8 can be changed to 2 cubed, and the right side, 1/2, can be changed to 2 to the power of negative 1. The left side, of course, we multiply these two. We get 2 to the power of 3x, and 3x must be equal to negative 1, which means x must be negative 1/3. 9 to the power of 2x plus 1 is the same as 27 to the power of x minus 1. We can replace the 9 with 3 squared and 27 with 3 cubed. So by the power rule, we multiply these two. So it becomes 3 to the power of 2 times 2x plus 1, which is 4x plus 2. And then 3 to the power of 3 times x minus 1, which makes it 3x minus 3. And again, we have the same base, namely 3. We must have the same exponent, namely 4x plus 2 must be equal to 3x minus 3. We move this, and we move this, and we get x equals negative 5. As always, you can check your answer, and checking takes place with the original equation only. We want to solve an We want to solve exponential and logarithmic functions. Here's the example to log base 5 of 2 plus log base 5 of 2x minus 1 equals log base 5 of 3x plus 1. Notice you have the same base, and reminding that everybody the domain of log functions, positive numbers only, so check for extraneous solutions. Meaning, if you end up with something, you have to check it with the original equation, making sure none of the arguments is negative. So that being the case, if all of them are logs, both sides, then you don't have to move things around. Make each side into a single log. So as you can see, for this one, I'm going to use the product rule number 5, and I make it log base 5 of the product of 2 and 2x minus 5. The right side doesn't change. Because they have the same base 5, they must have the same argument. So 2 times 2x minus 5 must be the same as 3x plus 1. And this one is 4x minus 10. This is 3x plus 1. Move things around, and x becomes 11. Log base 2 of x minus 4 equals 3. Anytime you have a single log and a number, or if you have a bunch of logs and a number, you bring it to a single log, then you go to the definition. 2 cubed is x minus 4. Of course, this is 8. Move this, plus 4, make it 12. Now, before we move on, I want to make sure you understand. Whenever you get your answer, you really have to check the arguments. For example, if I put the 11, we can't put it here, but if you put it here, this is positive, we are fine. If you plug in 12 here, 12 minus 4 is positive, it's fine. The argument must be a positive value. 4 times the quantity 10 to the power of log 2. So I hope you recognize number 4, b to the power of log x base b is x. So this, remember, log as the base 10, 10 to the power of log 2 is equal to 2. So 4 remains times 2 equals 8. 5 times 2 to the power of x is 3. To solve for 2 to the power of x, we're going to get rid of the 5. That means divide both sides by 5. Now, you want to see if there is any possibility that make both sides having the same base. This has same base 2. Can we make this having base 2? The answer is no. Therefore, we have no choice but to take a log of both sides, either common log or natural log. The reason why, because we want to get to x. So take a natural log of both sides. Now remember, ln of 3/5 is a number. But what happens to the left side? X becomes a coefficient and sits in front. Using the power rule. So what is x? Divide by ln 2. And this is an exact answer, everybody. The top, you could write it as ln 3 minus ln 5. If you don't, it's not a big deal. It is an exact answer here. Now, they may want a decimal representation. You use a calculator, and it ends up being negative 0.737. If they said 3 decimals, you go to the fourth one to make a decision. So it's important to know when to stop, when not to. All right, we are going to move on looking at more examples. 9 to the power of x minus 3 to the power of x minus 6 equals 0. Notice that 9 is 3 squared. Therefore, 9 to the power of x is 3 to the power of x squared. Now, if we let 3 to the power of x be represented by any variable except x, for example, u or m or z or y, your choice, then I hope you recognize this is u squared minus u minus 6. And this is easy factoring. You want two numbers. The product is -6. The sum is -1. So those are -3 and +2. And they result in two answers. U equals 3, U equals, or U equals -2. That means 3 to the power of x is either 3 or -2. So I hope you recognize this one as 3 to the power of x is 3 to the power of 1, and therefore x is 1. And 3 to the power of x equals -2 has no solutions because, as you recall, all exponential functions have a range of 0 to infinity. They are larger than 0. That's the reason. So x is 1. So there's only one solution, everybody. Log x base 2 equals 3 minus log x minus 7 base 2. Again, anytime we have a bunch of logs and a bunch of numbers, we bring all the numbers together, we bring all the logs together. So we don't have to do anything about this number, but this one we're going to move it to the left, becomes plus. So we have log x base 2 plus log x minus 7 base 2 equals 3. Now we're going to combine the two on the left side using the product rule. So it becomes log base 2 of x times x minus 7 equals 3. Now, whenever you have a single log on one side and a number on the other, you go with the definition of an exponential. So x times x minus 7 is 2 cubed, or 2 cubed equals that. Makes no difference. So this is, of course, x squared minus 7. This is 8. We move it to the left in order to bring everything to the same side for the sake of factoring. So we want two numbers. The product is -8. The sum is -7. So -8 and +1. They result in two answers. X is either 8 or negative 1. Now, you have to check, and you have to check only with the original equation. If I plug in 8, this is a positive argument. 8 minus 7 is 1, is a positive argument. It's fine. That works out. If I put negative 1 into the first one, it doesn't work. I don't even have to check here. So one more time. It doesn't work here because x can't be negative. So it's out. But just for the sake of argument, if it works out here, I have to check here too, okay? Log base 2 of x equals 3 plus log base 2 of x minus 7. Similar to that, and we do exactly the same thing. We move this one here, and we're going to move this one to the left as well. So move it. Becomes negative. And now, if I look at the left side, you can use the quotient rule, everybody. So this becomes log base 2 of x over x minus 7 on the left side. The right remains as number 3. Now, the left side is the single log. The right side is a number. Again, we go with the arrow. We say x over x minus 7 is 2 cubed or 8. We can do the cross product. 8 is the same as 8 over 1. So 1 times x meaning x equals 8 times x minus 7, meaning the right side is 8x minus 56. I can move the x to the other side, becomes minus x. And move the negative 56, make it positive 56. Divide both sides by 7. X becomes 8, or 8 equals x, makes no difference. I'm going to go back to the original equation. X is fine here. 8 is fine here. 8 minus 7 is positive 1. It's fine here too. So that's an acceptable answer. And you're done, everybody. We have the same situation. One side is a number. One side involves a bunch of logs. We are going to bring log x base 4 and log 7 base 4 together using, again, the product rule. So this is log base 4 of x times 7. X times 7 is 7x. And we are ready for the exponential rule. So 7x is 4 squared, or 16. X is 16 over 7. And if you put that into the original equation, this is 16 over 7, or positive value. That works out because you want to make sure all arguments are positive. You can further investigate and see that 16 over 7, when you multiply it by 7, you get 16. Log of 16 when the base is 4 is 2. Same thing, we can combine these two into a single log by using the quotient rule. So log x over 7 base 4 is 2. Again, we go with the definition. uh, 4 squared is x over 7, or x over 7 equals 4 squared, which is 16. And so if you multiply both sides by 7, you get 112. So I hope you see what I was trying to do here. If you look at A and B are almost identical, whether you have a plus sign or minus sign. The left side, you bring it into a single log. In this case, we had to use the product rule, but in this case, we had to use the quotient rule. Conceptually are very similar. Again, I'm reminding you of this. This is extremely important. Log base 3 of 4 equals 2 log base 3 of x. Now, one easy way is to make each side a single log. This time, we are going to use number 7 and move from right to left. In other words, we're going to put the 2 as an exponent for x. So the left side, we're not going to touch it. The right side, the 2 in front, which is a coefficient, using number 7, the power rule becomes the exponent. Now, we have log with the same base on both sides. Then their argument 4 and x squared must be identical. So x is either positive or negative 2. And clearly, when you go back to the original, not this one, original, because this one, negative 2 is fine. But with the original one, negative 2 is out. That's an extraneous solution that has been mentioned. What about this one? Again, on the left side, we have a bunch of logs, and on the right side, we have a number. So we are going to combine the left side into a single log using the product rule. Why the product rule? Because it's a plus sign. So log base 2 of the product of these two, x plus 2 times 1 minus x equals 1. And now we can go with the definition of a log. Going this way, that means 2 to the power of 1 is the product of x plus 2 and 1 minus x. Now, if we multiply these two, if you multiply the x, you get x minus x squared. If you multiply the 2, you get 2 minus 2x, and the negative 2x and positive x, they combine to give us negative x. Because we want to solve this, okay, we are going to move things around. First of all, we're going to get rid of the 2's on both sides. Then we can either move it to the left or just factor out the negative x, makes no difference. If we move everything to the left, both take a positive sign. Now, if we take the x out as a common factor, then we get two answers. X is either 0 or negative 1. So let's go back to the original formula equation, part B. If x is 0 plus 0 makes this one positive 2, so far so good. 0 make this positive 1, so far so good. So 0 is fine. Let's go with negative 1. Negative 1 plus 2 gives us positive 1. That's good. Negative 1 times negative makes it positive 1, and 1 is 2. So both of them are acceptable. So we did check both of them. You must check both answers. 8 to the power of x is 15. We are looking at an exponential function, exponential equation. We are hoping to get the same base on both sides. On the left side, we have the base 8. We can even get the base 2 Can we do that on the right? The answer is no. So what do we do to get to x? You have to take a log. You can take a natural log, you can take a common log, makes no difference. This time I'm going to take a common log of both sides. And now if I look at the left-hand side, using the power rule, I bring the x in front. And remember, log 8 is a number, some number. Of course, you have to use a calculator for that, but it's an exact number instead of an approximation. So when we do that, this is your exact answer. By the way, if we had taken class, if we had taken natural log here, take a look. Let me use a different color actually. If I take over here, if I took ln of the left and ln of the 15 over here, I would have ended up with ln of 15 over ln of 8. And again, by no means we mean a log 15 and ln 15 are the same. We are saying this ratio and this ratio are identical. Now, if you use a calculator and they said, okay, let's say, let's go with fourth decimal, then you have to go to the next one to make a decision. Again, what is this? This is an exact answer class. This one or this one. Exact answer, they're identical. To solve part B, we notice that on each side we have logs. Do we have to move things around? No. All we have to do is to make sure each side has a single log. The right side does, the left side doesn't. We're going to combine the left side using the product. So the left side becomes log base 3 of x times x minus 3. The right side doesn't change. We have the same base, we must have the same argument. So this is x times x minus 3, this is 10. Of course, this is x squared minus 3x. And we move the 10. We can factor, we need two numbers. The product is negative 10, the sum is negative 3, negative 5, and positive 2. The answer is x equals 5 or x equals negative 2. We must check with the original equation. If I put the 5 here, positive argument. If I put 5 here, 5 minus 3 is positive, so I'm fine. This is a number we don't have to worry about. If I put a negative 2 into the first one, it doesn't work. I don't even have to check with the second one. It fails here, so negative 2 is out. All right, we want to solve this, and we notice we have numbers on both sides, log on both sides. So what do we do? We are going to move 1 to this side, make it negative. We move negative log 5 base 4 to this side, make it positive. Of course, just to add up to 2. So that's pretty straightforward, everybody. All right. So what happens to the left side? I hope you see that in one shot. This is log x, this is log 5, this becomes log 5x, this is minus log 7. So anything that takes a that has a positive coefficient they get multiplied. So log 5x and then divided by 7. I hope you see that in one shot. If you don't, take a look at what I'm going to do here. You can rewrite this. Use a different color. As log base 4 of x plus log base 4 of 5 minus log base 4 of 7 equals 2, and write this part as log base 4 of x times 5 of 5x. And now if you combine it with this, you get this. Okay. Do you have to do it in 2 steps? It's your choice. I think it can be done in 1 step. Okay, but if it's up to you ultimately. Okay. All right. So what's the next step? Definition. 4 squared is 5x to the power of 7, or 5x over 7. 5x over 7 is 4 squared, which means 16. And so all you have to do, first multiply both sides by 7. 7 times 16 is 112. Finally, divide by 5. And that's your exact answer. If you put this number into this, it gives you a positive argument. So there is no other log involving variable x. So we are done because we just checked it. Let's continue by solving this exponential. The very first thing you ask yourself, can I make, this is 2 to the power of x minus 1, this is 5 to the power of 2x plus 3. Can I make both sides such that they have the same base? The answer is no. Either the same base or the same exponent. So when we can't do that, then how do we get to the exponent x somehow? You have to take a log. Natural log or common log. So if you take a natural log of both sides and use the power rule, in this case, x minus 1 becomes a coefficient, in this case, 2x plus 3. Now we are going to distribute, remember ln2 and ln5 are both numbers. But when you keep them as ln2 and ln5, those are exact numbers. Okay. And so this one is x times ln2. This one is minus ln2. This one is 2x ln5. This one is plus 3 ln5. So since we are solving for x, we are going to bring all x's together, all numbers together, which means this one must move this way. This one must move this way. They change sign. So we end up with x ln2 minus 2x ln5 equals 3 ln5 plus ln2. Of course, you can move them around anyhow you want. Notice on the left side, we can factor out the x. And we get x times ln2. When you take the x out, whatever is left, ln2 minus 2 ln5. And all you have to do, divide both sides by the parentheses ln2 minus 2 ln5. And there it is. Now, a couple of things I want to mention before we move on. Number one, when we did the moving here, you could have gone this way, and that becomes negative, negative, positive, negative, negative, positive. The other thing that, so it's important to know if you move things around differently, the answer in this format may look different, but they're identical. The other one is that what if I put log, that means common log, instead of ln? I want to show you that one also. If instead of ln you did the log, okay, everybody, this would become 3. Instead of ln 5, you would have log 5 plus log 2 over, instead of ln 2, you have log 2 minus 2, instead of ln 5, log 5. They don't look the same, but both of them, if you do the approximation, they will be equal to, again, roughly. Okay, this is exact, everybody. This one is exact. And of course, so is this one. And both of them are approximated by the same number, negative 2.186. So it's important to understand that what is exact, what is an approximation, and distinguish between the two. All right, we want to solve 4 to the power of x minus 2 to the power of x minus 12 equal to 0. And again, we should recognize that 4 is 2 squared. Therefore, 4 to the power of x is the same as 2 to the power of 2x. We can see that, therefore, if you let this one be represented by any variable except x, for example, m, this is m squared. So we have m squared minus m minus 12 equal to 0. We want to factor this. We want two numbers. The product is negative 12. The sum is negative 1. So negative 4 and positive 3. M is either 4 or negative 3. Therefore, we are going to replace this with what we have. 2 to the power of x is either 4 or negative 3. We've already discussed that. This can't be, because exponential functions have a range from 0 to infinity. So 2 to the power of x can never be negative. 2 to the power of x equals 4 means equals 4 or 2 squared, so x must be 2. So there's only one answer, everybody. X equals 2.